All right, welcome. This is the AP Physics workbook solution. Here we have Unit 6, Simple Harmonic Motion. The section is 6.E, Equilibrium on an Incline. Here's the scenario. A cart of mass M is attached to a vertical spring of spring constant K so that the spring stretches a distance x naught. When the cart is set into oscillating motion on the vertical spring, the period of the oscillation is T. The cart is then set on a smooth incline, theta, above the horizontal, and reattached to the spring. All right, so now that is on its incline, part A. The dot at the right represents the cart at rest on the incline. Draw a free body diagram showing and labeling the force, not the component exerted on the box. Okay, so this should remind you of the incline plane problem. Okay, right here on the right, if you would like to remember. Now, we have the force going down, which is force of gravity, mg. So goes down, force of gravity. Then you have the normal force, which is perpendicular to the surface. Then look at the spring force, right? The restorative force. Okay, it is displaced to. It's displaced left, so the restorative force is to the right. So force of the spring or the restorative force is to the right. Good. All right. So now you're going to derive a expression for the stretch spring L when the cart is on the incline in terms of x naught, theta, and any physical constant. All right. So we know that right here, this should remind you of what you were supposed to do. Okay. This is the force on the x direction is defined by this. Okay. And this is how it looks like when it's on the y. It's going to be the same way here. Okay. So we would say that the F in the y direction is going to be equal to 0. Okay. What are the forces that are acting here? Which is going to be the let's take a look. Force of gravity down, and what is going up against it is the spring force, negative KL. L is just referred to the distance. In this case, it's x naught. Okay, x naught is the length because it says it right here. The distance x naught. Okay, so here it would be like this. Okay, or you could set both of them to negative or both of them to positive. Okay, so you can write here kx naught is equal to mg. Okay, so spring force is equal to the force of gravity. Okay, the negatives and the negatives cancel out. Good. So if you want to solve for this, you can get k is equal to mg over x naught. You should see these in your previous problem. All right. Now, then we have f. The summation of f on the x are basically on the incline. Okay. If we treat, let me treat this, anything like this, is the x direction. Okay. If that makes sense. Okay. It's parallel. So this is x, or along the incline, and this is equal to 0, exactly like what we said here. And your two forces here, in this case, it was mg sine theta, but you have one more force. In this case, it was the what? Force of gravity, force of the spring. So you want to bring here, and you want to it should look something like that. Does that make sense? Okay, because in this scenario they didn't have an opposite force, but it does because it's a spring in this case. Okay, it should look like that. All right, so you should write that as the Fs, restorative force, minus mg sine theta, and this equals to 0 because it's at equilibrium. Okay, And you can solve for this if you would like. Fs is equal to mg sine theta. Okay. We know what the force of Fs is. Force of Fs is defined as Hooke's law. Okay. But in this case, you can make this positive when you bring it over. X naught, right? Because this is basically it's how it's being pulled. Okay. Or you could just use that as okay, L. Right. So L is going to be the stretch of the spring. Okay, so here it would be KL, right? Because it should be something like this. Okay, force of the spring is KL. KL is equal to, right here, mg sine theta. We know what K is. Do you see how K was from up here? Oh, do you see how K was from up here? That's the reason why we got K, right? So bring this in. This was K. Then we have L, which is this part. All right. That's how the substitution would look like. Okay. Divide mg over. You should have L is equal to sine theta over hold on, LG. I multiply, I multiply x naught, so it should be x naught here, right? Because again, if you want to do it, the inverse would be you are multiplying that. Okay, that's how you get that part. So L is equal to x naught sine theta. Okay, so does this equation make sense for when theta equals to 0? So let's see if that makes, let's see what that means. So L equals to x naught sine of 0. Sine of 0 is basically 0. So it should be equals to 0. Let's see if that makes sense mathematically. All right. All right, so I said yes, the equation makes sense because when the angle measurement equals to 0, when the angle measurement is equal to 0, that means the inclined ramp is just a horizontal surface. When the spring is on a horizontal surface, there's no force that is causing the spring to stretch. Mathematically speaking, sine of 0 degrees is just 0. That's what we did there. And if you would like to see how that looks like, here is the surface, here's the spring, right? Okay, there's nothing pulling it. Okay, does your equation make sense when theta equals to 0? Let's see if that works mathematically. L is equal to x0 sine of 90 degrees. Sine of 90 degrees is 1, so it should look something. L should be equal to x naught. All right, mathematically speaking, since 0 degrees is 1, when the ramp is at 90 degrees, then the ramp is completely vertically, which is the same thing as the mass hanging straight down. A mass hanging straight down is the length of the spring being stretched due to the force of gravity pulling it down. It should be something like this, right? That makes sense, right? The only thing pulling it down is the L due to the force of gravity. So yes, that makes sense. Okay. Part D. How does the new period of oscillation motion that could undergo on the inclined plane compare to the original t when hanging vertically? How does the new period change? Well, for a simple harmonic motion, the period t is independent of the amplitude, but depend on the stiffness of the spring, force of K, and the mass, the inertia mass. Okay? Right, so that's the core idea. So I wrote there's no difference in the period of oscillation. The period of oscillation of a simple harmonic motion only depends on the mass, inertia mass, and the spring constant, not on the incline angle. The incline angle doesn't do anything. Okay. All right. Next, the car is being pulled down the ramp so that it stretches here. All right, and it gives this motion of the graph. This motion of the graph here, this is a cosine Yeah, this is a cosine wave. This is a cosine wave. All right. All right. So um, we know that. Right. So if you think about it, okay, let me give you some notes. Okay. So let's go over the calc version first. So if this is the original displacement, which is a sine wave, so in this case it starts with sine, okay? Right? The derivative of the displacement will give you its velocity. So calc-wise, that is doing the derivative as a function of time. So here, you're just going to take the derivative of sine omega t as a function of t. So t just becomes 1, but you have to do the chain rule. What's left on the inside? W. So it just becomes the amplitude. Okay, here it just uses d. So, but the amplitude omega cosine wt. That's how you get velocity. Okay, so it becomes a cosine wave. Now, if you take the derivative of that again, you have to do the chain rule to deal with that omega. Okay, the omega comes out, the t becomes a 1, and the inside stuff, it becomes a sine. Again, this is a perfect example of the chain rule. Okay, so you're doing the chain rule to go from uh, to get the derivative of displacement to velocity, velocity to acceleration. Okay? Now, if you look at this, notice that this graph, right? If you move it over to the left, look, doesn't it look exactly the same? Okay? So if you move this over just 90 degrees, it should look what? Exactly the same like the velocity, right? But now, what about if you just move it a whole 180 degrees? Okay, one whole 180 degrees. It looks like the acceleration. So an easy way to memorize it is this. If the original is a position versus time, the velocity is at any time it's just 90 degrees out of phase with the position. So you just move it over 90 degrees. Acceleration would be another 90 degrees. Okay, so to get the acceleration, if you have position, to acceleration is 180 degrees shift. Velocity would be just 90. Okay, so if you take a look, this is the sine wave. Okay, this, its complete oscillation occurred from here to here. So this is at 2 pi. That means this is at pi. So this is at pi and a half. This is 180 degree. This would be, no, sorry, this would be 360. This would be 180. This would be at 90. So it starts here. You're just going to do a horizontal shift. Okay, so it should start here for the velocity graph. Okay, so start down, exactly like this, down, then goes back up, goes up here. All right. Sorry, looks ugly. So it should like this. Here, up, down, up, down, up. There you go. Okay. So it's just horizontally shift. All right. Here to get acceleration, we do a 180 degree shift. So it's like this. Okay. Delete that. It's exactly like this. Okay. So let me graph this copy. Let me show you. It's like this. So it should look something like that. That makes sense, okay? Alright. So looks like this. Up, down, up. Sorry, that's horrible. Down, up, down. Okay? So again, from the cosine, this is going to be a this is a cosine wave, so this is going to be a sine wave, but it's going to be a negative. This is going to be a sine wave. Um, this is a sine wave, but you see how it's flipped. Okay, so this is going to be negative sine. Then this is going to be a cosine, but also negative because cosine, alright, looks like this, but this is also a cosine, negative cosine wave. Okay, that should make sense as we go over the derivatives. All right. So, but just remember from cosine, so from the position to the velocity wave, it's just a 90-degree horizontal shift. From here to here, it's also just a 90-degree horizontal shift. Okay? Likewise, so this is to the right. Okay? Sorry, to the left. Now, if you want to think about from acceleration to velocity, right, this would go to 9 degrees to the right. Here, from velocity to position wave, you would go 90 degrees to the right. Okay, same idea. All right, so there you go. Those are all your solutions.